Welcome to the training module on a study on high-precision op-amps by Microchip Technology. This training module gives you an introduction to high-precision operational amplifiers, including their key features, basic block diagrams, and application. Microchip Technology's MCP605X family of operational amplifiers have low input offset voltage of about plus or minus 150 microvolts and a rail-to-rail input and output operation. This family is unity gain stable and has a typical gain bandwidth product of 385 kHz. The device operates with a single supply voltage which can be as low as 1.8 volt whilst drawing a low quiescent current of about 30 microamps per amplifier. These features make this family of op-amps well suited for single supply, high precision, battery-powered applications. The MCP605X op-amps are also suited for conditioning sensor signals in battery-powered applications. An op-amp can simply be defined as an analog gain block with two signal inputs, two power supply connections, and one output. The ideal op-amp description can be separated into four basic categories: input, power supply, output, and signal transfer. The input stage of the op-amp has two terminals, the non-inverting input or Vin positive and the inverting input or Vin negative. For an ideal voltage feedback amplifier, both inputs need to be matched, thus resulting in no leakage current, infinite input impedance, infinite common mode rejection, zero noise, and zero offset voltage between the terminals. This diagram shows the op-amp's internal block diagram. As you can see, there are three distinct stages. The first stage, or the differential input stage of the amplifier, must have very high input impedance. This causes the op-amp to draw very negligible amounts of input current. The second stage, or gain stage, is mainly responsible for magnifying or boosting up the input signal and sending it to the output stage. The third is the output stage, which delivers current to the op-amp's load. It may or may not have short-circuit protection. This slide shows both an inverting and non-inverting amplifier circuit. In the inverting amplifier configuration, our signal or Vin flows through the negative input and therefore has the opposite sign to the output. The negative feedback is provided by the resistor R2, which connects the output to the input. In the non-inverting amplifier configuration, the analog input is fed through the positive input terminal. The equation for the gain is shown as VL divided by Vin. A gyrator is a four-terminal or two-port device that is designed to transform a load impedance into an input impedance, and where the input impedance is proportional to the inverse of the load impedance. The gyrator network can be used to transform a load capacitance into an inductor. The primary use of a gyrator is to simulate an inductive element in a small electronic circuit or integrated circuit. The primary application for a gyrator is to reduce the size and cost of a system by removing the need for bulky, heavy, and expensive inductors. Gyrators typically have higher accuracies than real inductors. This is because of the low cost of precision capacitors over inductors. This page shows an instrumentation amplifier circuit using two MCP6052s. It works well for applications requiring rejection of common mode noise at higher gains. An instrumentation amplifier is a type of differential amplifier that has been outfitted with input buffers, which eliminates the need for input impedance matching and thus make the amplifier particularly suitable for use in measurement and test equipment. The most frequent application for comparators is the comparison between a voltage and a stable reference. Because comparators have only two output states, their outputs are near zero or near the supply voltage. Bipolar rail-to-rail comparators have a common emitter output that produces a small voltage drop between the output and each rail. This is the MCP6XXX amplifier evaluation board. The board is designed to support inverting and non-inverting amplifiers, voltage followers, inverting and non-inverting comparators, as well as inverting and non-inverting differentiators.